In this video, we are going to talk about surface integrals of vector functions. In our last video, we talked about surface integrals of scalar functions. So both of them involved surfaces, but now instead of scalar functions, we will do vector functions. This is our first overview slide, which we will go through briefly. This video has a second overview slide, which we will also go through briefly. And then we'll go back and cover our overview slides in more detail and follow up with more examples. As I had mentioned, this video covers surface integrals of vector functions. So the idea is we have f, and that's a vector field defined on S, the image of a parameterized surface. The surface integral of f over the surface is defined using this formula. It's a double integral, and it's over a two-dimensional domain, which is in the u and v plane. And then we have f dotted with tu cross tv, and tu and tv are our tangent vectors in the u and v direction on our parameterized surface phi. This is phi. So the steps we're going to use to evaluate the surface integral is first to parameterize our surface phi. Then we're going to write our vector field f. In terms of phi, we're going to use function composition for that. Then we're going to calculate our tangent vector in the u direction, our tangent vector in the v direction, and then come up with a normal vector, which is tu cross tv. And finally, we'll plug it into our formula for our double integral. This first example illustrates those steps. If we have a vector function f equals xy, z minus 2y, we want to evaluate the surface integral f dot ds over the helicoid phi equals r cosine theta, r sine theta, and theta, where theta goes between 0 and 2 pi and r goes between 0 and 1. The first step is to parameterize our surface phi. So phi of r theta is equal to, well, actually the parameterization has already been done for us. Phi of r theta equals r cosine theta, r sine theta, and theta. Theta goes between 0 and 2 pi, r goes between 0 and 1. This part here is something you don't want to forget to do. This part later becomes your limits of integration. Our second step is to write f in terms of phi, in other words, our function composition. So f, and then we plug in phi, and phi is r cosine theta, r sine theta, and theta. Here is f. So f is going to be our x-coordinate, which is r cosine theta, and then our y-coordinate, which is r sine theta, and last, our z minus 2y. So z will be our theta, and minus 2y, that would be minus 2r sine theta. The third step is to calculate tu and tv, and then the normal, which is tu cross tv. So looking at, in this case, our phi is parameterized by r and theta, so we will calculate tr and t theta. Derivative, partial derivative with respect to r, so considering theta a constant, will be cosine theta, sine theta, and then with respect to r, theta would be 0. Partial derivative with respect to theta, now considering r a constant, will be minus r sine theta, r cosine theta, and 1. And then we can calculate the normal by doing the cross product, and we get sine theta, cosine theta, and r. Finally, we can plug into our double integral. So we have our double integral, and we integrate. Let's see, we're going to do d theta first. So on the inside, our limit should go from 0 to 2 pi, and dr on the outside, so r will go from 0 to 1. And then we need f, which we have over here, r cosine theta, r sine theta, and then theta minus 2r sine theta, and then last, our cross product, which we have here, sine theta minus cosine theta, and r. From there, we do the dot product and we take the integral. Looking at our next overview slide, there is a second form of this surface integral, and that is that we can use the normal. So we take our formula that we have from the previous slide, and then we use tu cross tv, but then we divide by the length of tu cross TV. So we normalize this. This will be our vector normal. But then, because the formula needs to stay the same, we multiply by TU cross TV, the magnitude of TU cross TV. Now, it might seem kind of silly to divide and then multiply like this. Obviously looks like more work than just calculating this, but the idea is if you happen to know the normal of the surface, and you will for surfaces like a sphere, because the normal is going to be pointing directly out, or maybe cylinders, you'll also know the normal, it'll be pointing out, as well as cubes. So if you happen to know the normal, it might be the case that then this formula here will be a quick and easy way, or actually you would use this formula here, would be a quicker and faster way of performing your integral. The next topic of this slide is flux of f. So we can give this surface integral of vector function a physical interpretation, and it's the net quantity of fluid to flow across the surface per unit of time. That is, it's the rate of fluid flow. And this integral is also called the flux of f across the surface. And in cases where f represents an electric or magnetic field, the integral is also commonly known simply as flux. Faraday's law relates flux of a vector field to circulation or current in a bounding loop. And this is the historical and physical basis of Stokes' theorem, which we will cover later in this book, in our book. Last is a note about our oriented surfaces. So an oriented surface is a two-sided surface where one side specifies as, we specify it as the outside or the positive side, and the other side is the inside or the negative side. So for an oriented surface, we're pointing outside, that will be considered the positive side. So if we have a sphere, we're pointing outwards towards space. That would be the outside kind of orientation. At each point x, y, and z on S, there are two unit normal vectors, n1 and n2. So one pointing outside, one pointing inside. And n1, if it's outside, is equal to the negative of n2, which is pointing inside. And each of these two normals can be associated with one side or the other of the surface. Of course, this assumes the surface has two sides, unlike a Mobius strip, which has only one side. And here's the illustration, the Escher illustration of a Mobius strip. It's a surface with only one side. You can see this ant here crawling on the Mobius strip. If it keeps crawling, it crawls around, and it actually ends up on the underneath side, so to speak, without actually having to think of crossing somehow to the other side of the strip. And you can make a Mobius strip if you have a strip of paper, and you attach, do a twist and then attach the two ends together, you will have a Mobius strip. We say the parameterization of a surface is orientation preserving if the vector TU cross TV, that is the normal, points away from the outside. And we call it orientation reversing if it points towards the inside. And we have this theorem if we have two parameterizations. If they're two orientation preserving parameterizations, then their surface integrals will be equal. If one is orientation preserving and the other is orientation reversing, then they're equal with the difference of a negative sign. That is our quick overview of the material. So we're going to go through the material in more detail with more examples. In fact, I think there are 4 more very complete examples. We will start with this main formula you will be using for surface integrals of vector functions. The first thing to notice in this formula is the capital F, and that's to denote that this is a vector function. So it's important that you notice these capital F's and the lowercase f's, they mean something. Capital F means you take a number of variables and you map it to R3. So in other words, here's an example. You have x, y, z is mapped to an x coordinate equal to x squared plus y, a y coordinate equal to x times y, and a z coordinate equal to 2 times your z plus 3. And so again, it takes a vector and it gives you another vector in R3. So this vector has magnitude and direction. A scalar function, on the other hand, which we always denote with a lowercase f, maps to a real number. So you can have x's and y's in your mapping. So f of x, y, z can equal something that has x and y terms, but they all get added together. So in the end, you just have a number. You have a magnitude, no direction. Our last video talked about surface integrals of scalar functions. This video will deal with vector functions. The next thing to notice up here in our formula is this capital S in the ds, and over here where I have this big picture, this capital S tells us that this is a surface integral. In our previous video, like actually not just one video back, but I think 2 videos back, we did line integrals, and that was designated with a lowercase s. So these little details are important in that if someone asks you to evaluate this this surface integral, that you notice if they just give you the formula and say evaluate this, you'll know that this is a surface integral. There'll be other hints along the way, such as the fact that you'll be given a surface and not just a curve or a path. But you have to pick up on all these little things that it'll help you out. I have written our formula that we will be using for our integral of a vector field over a surface. And I did write, for comparison, a scalar function over a surface, the integral of a scalar function over a surface. Again, remember this means f maps to a real number. This, a capital F, the vector field, maps to a vector. So it's very similar. What you'll see, if you recall, when you had a scalar function integrated over a surface, you would compose your scalar function with your mapping and then multiply by the magnitude of your normal vector, which was equal to your 2 tangent vectors cross-multiplied. Very similar here. You have your vector field is going to be composed with your mapping, and then you're going to dot it with your normal vector, which is your 2 tangent vectors crossed, multiplied. So obviously here, when you have a scalar, you can't dot a scalar with a vector. But now that we have a vector field, we can. And so we'll be using the dot product. A comment on this function composition. The thing about f is it defines this vector field over all of R3. So all of R3, it tells you for each point in R3 it associates a vector. But the thing is you're only concerned about the vector field on the surface. You're only worried about integrating these points here that are on the surface. So you actually don't really care about these things that aren't on the surface, but only the vector field that's on the surface, and that's why you do this function composition. One last comment I would like to make. Okay, one last comment. I originally made these videos for my daughter, and at the time I couldn't remember if this was called phi or phi or something else. I couldn't remember the name of the Greek letter, so I said, well, it looks sort of like the green lantern symbol, and so let's just call this the lantern function. And so sometimes I'm still in the habit of calling it the lantern function, and so it might still be in the video. So now you'll know what I'm saying. But I'm also going to warn you, no one else, except maybe my daughter, will know what you're talking about if you say the lantern function, because everyone else knows this as phi. And so, just be warned that you don't pick up on my bad habit. We will start doing a bunch of examples in just a minute, but I'm going to say I broke up this formula into a number of steps. The first is to parameterize your surface, your phi. And if you recall, your surface is considered, well, you start off in the UV plane, and so you have a domain that's in the plane, and then your parameterization, your phi, will take this portion of the plane and map it into 3D space. So your surface is equal to your phi of your domain D. The next step is to write f in terms of phi, that is, do your function composition. And recall, the reason why you do this function composition is f will associate a vector with every point in your 3-dimensional space, but you're only interested in f and integrating f that is on this surface. So you do the function composition. Next, you're going to use your mapping to calculate a tangent vector. So you're going to take hold u constant and see how that maps over here. And you'll get a vector that's on your surface, and then you'll also hold v constant, and you'll get another vector on your surface, and the cross product of these two vectors on your surface will give you a normal. So you're going to calculate t with respect to u, t with respect to v, and then do the cross product. Finally, you're going to plug in these components into your formula. So your f composed of f composed of phi, and then dotted with your normal vector. An example will make this more clear. So we're going to let our vector field be equal to x, y, z minus 2y, and we're going to evaluate the surface integral over the helicoid, which is parameterized by r cosine theta, r sine theta, and theta. Our first step is to parameterize our surface phi, and in this case it's already been done for us. So we copy that down, as well as including the limits of theta and r. And copying this down as well will make it easy when we plug into our double integral. These ranges will become the upper and lower bounds of our integral. Next, we evaluate our vector field f composed of our mapping function. So if I plug in for x, y, and z, again, I'm only interested in the x, y, and z that are on the surface. So I plug in the relationship x, y, and z that is given to me by my surface mapping. So I have f of r cosine theta, f of y r sine theta, and f of theta. My f is equal to x, so that's nice, it just kind of moves over. Y, that kind of moves over. And then z minus 2y. So here's my z value minus 2y. Now we are ready to calculate our tangent vectors. Here we have tu and tv, but our parameterization of our phi is in terms of r and theta. So we will first calculate tr, and that is to take the partial derivative with respect to r, so theta is considered constant, so we'll get cosine theta, sine theta, and theta is a constant, so the derivative will be equal to 0. Next, we'll take t theta, so we'll consider theta our variable and hold r constant, so we'll get minus r sine theta, r cosine theta, and 1. We can now calculate the normal, which is tr cross t theta, and you can verify my work, and it should come out to be sine theta, cosine theta, and r. And now I'm ready to plug in to my double integral. I have my limits of integration here. So theta goes between 0 and 2 pi, r goes between 0 and 1, and then I dot my f composed with my lantern function, and I dot that with my normal, which is tr cross t theta. And the rest is just integration and plugging in. Now we're ready to do a few more examples, and the first one is to compute the surface integral of the radial vector field r of xyz equals xyz over the surface of a unit sphere. So here, r of xyz is the radial vector field, and it is a lowercase r because that's how it's usually denoted, but you can tell it's a vector field because it gives you something in r3. And it's radial because you can consider it radiating out from the origin. And we're going to integrate this vector field over a unit sphere. The first step is to parameterize our unit sphere. And one thing you will notice is this parameterization is very similar to how we parameterize spherical coordinates, with the exception that rho is equal to 1 here. And the reason rho is equal to 1 is because we only want the surface of the sphere. We do not want the interior of the sphere. We're not integrating over the entire volume, but just the outside surface of the sphere. So rho is equal to 1. And again, if we had let rho vary from 0 to 1 like we normally parameterize a surface in spherical coordinates, we're also getting the interior of the sphere. But because we're doing a surface integral, rho is equal to 1. And hence our parameterization becomes cosine theta sine phi, and cosine phi. So it's only dependent on theta and phi. Again, rho is held constant at 1 in this parameterization. If the sphere had a radius of 2, then our parameterization would have been 2 cosine theta sine phi, 2 sine theta sine phi. Sorry, I had to squeeze the 2 in. I forgot to write it. And then 2 cosine theta. So we continue on with the next step, which is to compose our vector field with our mapping. Again, we're only concerned about our vector field when x, y, and z satisfy the conditions that they are on the surface, which is why we do this function composition. And so where is my function f? Oh, my r is just equal to x, y, z. So it's just the same thing as your mapping, cosine theta, sine phi, etc. The third step is to find the partial derivatives. So I have my mapping here, and my first variable is theta. So I take the partial derivative of my mapping with respect to theta, and then partial derivatives with respect to the second variable, phi, is over here. I do the cross product, and here is my normal vector. And next is to plug into the double integral, but because of this dot product with f and the normal is kind of messy, I thought I would just do this first and then simplify it before plugging into the integral. So here is my f composed of my mapping, and here is my t theta cross t phi, and I'm going to dot them together. Here I have my cross product, which actually doesn't look too complicated, but we do need to simplify it before doing the integration, because if you look at this, when you want to integrate the cosine squared theta times sine cubed phi, and you can't simplify it, you'd have to do something to this sine. When you're integrating with respect to phi, you're going to have to do something with this sine cubed phi so that you can integrate it. And in particular, you would have to take sine cubed phi equal to sine theta 1 minus cosine squared phi, and then convert the cosine squared phi using your half angle formulas, which I'm not going to do now, because what I'm going to do instead is simplify this. So what you want to remember, and this is important, or I feel like it's important, it'll save you a lot of trouble in having to do really complicated integrals, is when you're in spherical coordinates, is when you have a sphere, you want to remember you can pull out a sine phi. Once you do that, you can see how I can simplify everything down to a negative sine phi, which is much nicer to integrate. Okay, I eliminated all that extra simplification just to save myself some space so I could do the integral. So now I'm ready to plug in, and I have my limits of integration here. Theta goes from 0 to 2 pi, and phi goes from 0 to pi. I have my f cross my tangent vectors. So here it is. The rest is just integration and calculation. One comment I do want to say is because we talked about flux, or we talked about which flux is the same thing as flow, because it's negative, that indicates flow is inward towards the center of the sphere. A positive flux or flow means things are escaping the sphere. I shrank all these calculations down and put them here for reference because what I wanted to do next was to redo this problem using this normal form of the formula. And if you recall, the time that I feel like that this is helpful is when the norm is something obvious. So in this case for a sphere, the norm is pointing outwards. So outwards from the sphere is the norm. And to normalize or to make it unit length, you just need to divide by r, because remember r is the square root of x squared y squared plus z, and r in this case is 1. So for our problem, the norm is just equal to x, y, and z. Now I can do f dot r norm. In this case, f is just equal to x, y, z. Our norm is x, y, z, so this is the dot product. I can now set up my integral, but I can look at this and realize that this is an easy integral to do in spherical coordinates. But one thing I need to remember is when I change to spherical coordinates, I need to multiply by the Jacobian for spherical coordinates. I will go over the calculation for the Jacobian in just a minute, but for now I'm just going to finish my integration. So I have x squared plus y squared plus z squared. This is just equal to rho squared. This is just the radius. And then over here, my rho squared sine phi is just my, actually sine phi is just the Jacobian for spherical coordinates. And one thing I'm going to remind you is the Jacobian that you always use the positive, the magnitude of the Jacobian. I have my limits of integration for spherical coordinates, and the rest is just integration and calculation, and I get the same answer. And then here is just kind of a quick review on how to calculate the Jacobian for spherical coordinates. The Jacobian is just the first coordinate you have, the x coordinate. You take the derivative with respect to the first variable. In this case, I did with respect to rho, and then you take it with respect to theta, and then you take the derivative with respect to phi. And then the second row is the same thing except for this second coordinate, the y coordinate. Derivative with respect to rho, with respect to theta, with respect to phi, and then the last z coordinate, derivative with respect to rho, with respect to theta, with respect to phi, and this is a determinant. You calculate the determinant, and the Jacobian that you plug in is always positive. And that's it for this example that we have done two different ways. We used the regular formula here, using the normal, which is the cross product of the two tangent vectors, and we also used the normal form over here. When we did our change of variables, we needed to incorporate the Jacobian. These formulas here that involve the TU and the TV, you'll never need a Jacobian in these formulas because all of that is kind of already baked in. Our next example is to compute the surface integral of this vector field x squared y, and y over the surface of a cylinder of radius 1, and it's bounded by z equals 1 and z equals -1. So this bottom surface here, S3, is at a height of -1, and this top surface here, S2, is a height at z equals 1. And the trick to this problem, or the important thing to this problem, is to realize that this surface, we will have to parameterize the kind of the lateral surface of this cylinder separately from the top and the bottom surface because they are different in nature. So S1, kind of the lateral surface of this cylinder, our radius is fixed at 1, again because we only want the surface of the cylinder. I'm laughing because I had written sphere originally because I was thinking of our last example, which is similar. We only want the surface of the sphere in our last example, so we held rho, the radius, equal to 1 or constant. Here, we only want the surface of the cylinder, so r is equal to 1. And again, the same idea. If we let r vary between 0 and 1, we would also get the interior of the cylinder, but we don't want the interior. We only want the surface. So our mapping then only depends on theta and z. So we have 1, again, r is constant, cosine theta, 1 sine theta, and z. Theta is going between 0 and 2 pi, and z is going to be between -1 and 1. That will give us our cylinder of height 2. I'm just going to compare those to the surfaces for S2 and S3. So S2, we're going to consider the top surface of the cylinder. In this case, z is held constant because z is at 1. So we parameterize the entire circle, 0 to r cosine theta, r sine theta, z is 1. Theta goes between 0 and 2 pi, and r goes between 0 and 1. And I just want to emphasize, in this case, we're letting r go from 0 and 1 because we really do want the entire circle. If we didn't do that, if we only let r, if we kept it held at 1, we would only get this blue outline of the circle. But the surface of the can includes the entire top part of the circle. Similarly, S3, z is held constant at -1, and we want to parameterize the circle, the bottom surface of the can. So we have theta r. R goes between 0 and 2 pi, and theta goes between 0 and 2 pi, r goes between 0 and 1. I will compute S3, the surface integral of f over S3. I'm going to leave S1 and S2 as a review problem for you, but I will give you the solutions afterwards. I believe it's very doable because we've already discussed the parameterization. So when the review problem comes up, don't forget we've already determined the parameterization for our mapping. Our first step is done. We did the parameterization, so now we're ready to write f in terms of phi. So f, I plug in phi over here into f, so I have my r cosine theta, my r sine theta, and my -1 from phi. Plugging that into f, and f is over here. It's the first coordinate is x, y squared, so I'm going to take my r cosine theta times the square of r sine theta. So I'm going to get an r cubed, a cosine theta, and a sine squared theta. For my second coordinate in f, I have x squared y. So now I'm going to have r squared cosine squared theta times r sine theta. So that will give me an r cubed cosine squared theta sine theta. And finally, my last coordinate is just y, which is r sine theta. I calculate my partial derivatives with respect to r and theta. I do the cross product and I get 0, 0, r. And then I can plug in into my formula. So I have theta going between 0 to 2 pi. Where did my d theta go? This should have a d theta at the end. And then my r goes between 0 and 1. This should have a dr at the end. And when I do my dot product, this goes away. My second term also gets dotted with a 0 and goes away. And so I'm only left with r squared sine theta. Performing the integration and then also plugging in, I get 0. I've put aside all these calculations here to give me some space because this top surface here is very easy to see what would be normal, what's perpendicular to something that's kind of in the plane of z equals 1. The normal is going to be equal to something pointing upwards. In particular, my normal, I'm at S3. So what's normal to this at the bottom? And again, remember our positive orientation for a surface is something that points outwards, away from the surface. So in this case, I'm going to be pointing down. So my normal is going to be 0, 0, 1. So now I can use this in my normal formula. I have my vector field F dotted with my norm, and it leaves me with only negative y. I set up my integral, and I plug everything in. I could have switched to cylindrical coordinates, but there was only a y, so I didn't feel the necessity to do that. But you can see I still get the 0 answer, which agrees with my previous results. So that's good. We've done this problem two ways. The first way, using the normal equals to tu cross tv. And the second, and using the parameterization. And the second way is just using the normal form. And I did want to mention at some point, if you decided you did want to convert to polar coordinates, you can do that. Just remember you need the Jacobian, and the Jacobian of polar coordinates is equal to r. I have that quick calculation of the Jacobian for polar coordinates over here for you. Our next problem is f is equal to xy, and then the square root of x squared plus y squared, and we want to compute the integral of f over the surface z equals 2 minus the square root of x squared plus y squared. And also we have this surface bounded by the plane z equals 0 and z equals 1. The first thing we want to do is kind of get a feel for what this surface is, so I went ahead and graphed it here. To give you an idea of how I got this graph, I looked at this part of my equation right here, where z equals, if we didn't have the negative sign, we didn't have the 2 minus, it would be z equals x squared plus y squared, okay, square rooted. But essentially, I looked at my level curves. What does my level curve of this form look like? And when z is equal to 0, I have my single point at the origin. When z is equal to 4, what I have over here at z equals 4 is a circle of radius 2. As we go up higher on the z-axis, when z equals 9, I have a circle of radius 9. So I have this sort of cone shape, and it is a cone rather than a paraboloid because of this, the square root. To relate this back to our original equation, this minus sign in front of the square root x squared y squared flips the whole thing over in this way. So the bottom of the cone is here. And at this point, the top of this cone, if you want the base to be, how do I want to say this? When you flip this over, you're going to have z equals 2 here. And then at the bottom, you're going to have the circle x squared plus y squared is equal to 4. The other thing you have to realize is now we want to bound it by the plane z equals 0 and z equals 1. So at z equals 0, that's fine. We still have this circle, x squared plus y squared equals 4. But at z equals 1, we take the top half of the cone off, because remember the cone goes all the way up to z equals 2. So we're going to take it off, and we're only going to kind of integrate the rest of this kind of tree stump shape. Here is the surface we are integrating. Now I need to parameterize my surface phi. But now our phi is expressed as a formula z equals something in terms of x and y. So to parameterize the surface, we just have x, y, and then we plug in our formula for z, 2 minus square root of x squared plus y squared. Now, looking over here on my domain, I'm going to have my x goes from negative 2 to 2, and my y is the other part. It's basically using z equals 0. I plug that in here, and then I'll get y is equal to negative square root of 4 minus x squared to positive square root of 4 minus x squared. I put in my boundaries that the radius is going to go from negative 2 to 2, and then I have this kind of in the circle. If I look at this in the plane, then y goes from, at z equals 0, y is going to go from negative 4 minus x squared, and then square root of 4 minus x squared, from the negative to the positive. Next, I will compose f with my mapping. So f composed of phi, so I plug in phi, x, y, and 2 minus square root of x squared plus y squared into f. F is over here, our function x, y, x squared plus y squared square rooted. So x, I just move over my x. Y, I just move over my y. And then next I need x squared plus y squared and then square rooted. So this is x squared plus y squared square rooted. I compute my tangent vector with respect to x. So here is x is equal to 1. With respect to x, this is 0. And then this with respect to x is negative x over square root of x squared plus y. Similarly, we have our tangent vector with respect to y. And then we get our normal. We cross our two tangent vectors to get our normal. And this is our solution. I've written my cross product over here just to make some more space. I set up my integrals using my limits here. I do my f. I do my cross product, and then I dot them together. It looks kind of ugly here, but when you dot it together, you get an x squared on the top, a y squared on the top, both over the same denominator. And then you have this square root again here. So when you simplify it, it isn't too bad. I also pulled this 2 from here out in front. And then I decided to change to polar coordinates. So I have my 2 out in front. Oh, and I forgot, the cone, actually the r, the radius is 2, but it stops at radius equals 1 because we don't go all the way to the top. So our radius actually doesn't go to 0. That was a mistake there. It only goes from 1 to 2. Our theta goes from 0 to pi. This here in polar coordinates is r, and we need to multiply by the Jacobian, which from our previous slide we saw is equal to r. So remember, at any point you can decide you want to change coordinate systems. It doesn't have to be at the beginning. Just remember you need the Jacobian whenever you do that. And the rest is integration and calculation, and here is my final answer. To review what we've gone over, we are calculating surface integrals of vector functions, and we use this formula here, and I've broken this down into 4 steps. First is to parameterize this surface that we're integrating our vector field over. The parameterization we call phi. We write f in terms of phi, so that our vector field that we're integrating, we do the function composition of f of phi. Next, we calculate these tangent vectors of phi. So if phi is defined on uv, we do the partial derivative with respect to u, the partial derivative of respect to v, and then we calculate the normal to the surface by doing tu cross tv. And finally, we plug in these components into our double integral. We use this here, this this vector field xy z minus 2y, and we integrate it over this helicoid, phi equals r cosine theta, r sine theta, theta going between 0 and 2 pi, and r going between 0 and 1 as our example. The first step was to parameterize our surface phi, which was given to us in this example. So we have phi of r theta is equal to r cosine theta, r sine theta, and theta. Theta between 0 and 2 pi, r between 0 and 1. We do our function composition. So we have f of phi. So plugging in phi, we have r cosine theta, r sine theta, and theta. Plugging that into f, which is equal to x. So our first term is r cosine theta. Then we have y. So our next term is r sine theta. And last we have z minus 2y. Our z term is theta. And then minus 2y. So that'll be minus 2r sine theta. We calculate the partial derivative of our mapping with respect to r, treating theta as a constant. We get cosine theta, sine theta, 0. And now the partial derivative with respect to theta, treating r as a constant, we'll get minus r sine theta, r cosine theta, and 1. We calculate the normal by doing the cross product. And then we plug everything in to our formula here. So we're taking the double integral with respect to theta and r. So here we have, with respect to theta and r, theta goes from 0 to 2 pi, r goes from 0 to 1. We have our f composed of phi dotted with our normal vector, and the rest is doing the dot product and the calculations and the integration. We had this normal form, which is useful if and can simplify calculations if we know the normal. This is especially true if you have a normal pointing out. So like if your surface is a sphere, your normal can be the radial vector, or if your surface is a cylinder or a cube, often the normal is easy to figure out. We also talked about the physical interpretation of the surface integral, and that is the idea of flux. It's the net quantity of fluid to flow across the surface per unit time, or the rate of fluid flow. And when you have a positive integral, that means fluid is flowing out. And if it's negative, that means fluid is flowing in. We also talked about orientation of the surface, and essentially what we said is that the positive orientation is oriented with pointing outside, outwards into space. And the other side is negative. That's when we're pointing inside, toward the inside of the surface. For review, I have these two problems here for you to work. If you remember, for the cylinder, I left S1 and S2 for you to try, but I did start you out with the parameterization. I have a second problem, is to let f of xyz equal xyz. This is the radial vector field, and I did use a capital F. Calculate the surface integral over the sphere of radius a. So a is the radius, and we want to do this two ways. One, using our normal equals tu dot tv. So this normal method up here. And then second, using the normal, the dot n normal form. Pause the video, and when you come back, I'll have just a couple of quick comments and then solutions for you. Here is the solution for the cylinder, and at this point in my integration, I did use this double angle formula, which I put in blue here. This is the solution to the second problem, and two things I will comment on is first, the radius here of our parameterization of the sphere radius a. We set the radius equal to a. We don't let it go from 0 to a because we only want the surface of the sphere. The second thing, when I was simplifying this dot product and I had this sign cubed, because I know it's a sphere, I know it's useful to factor out the sign of phi, and that way I can simplify this inside. If you did not see this, you can use this sign cubed, you could use this formula here, and then for the cosine squared, you can simplify it using the half angle formulas from trigonometry. Here, the second way, the second method, using the normal method, meaning using the normal, the orthogonal vector, I have my f function, x, y, z, and then my normal for a sphere is the radial vector field. So that's also just x, y, z. I normalized it by dividing by a. So I made this a unit length vector. And now what you can see is when I do the dot, I'll get my x squared, my y squared, and my z squared over a, but x squared plus y squared, z squared is just a squared. This is just the radius squared. So then I can simplify this to a over the surface integral ds. And this part here is just the surface area of the sphere, because whenever you have the 1, you're going to get the surface area. If if it's a volume, the 1 would give you the volume. If it's a path curve, it's the length of the curve. So the 1, in this case, because it's a surface integral, will give you the surface area of the sphere. So this is a times the surface area of a sphere, which would give you 4 pi a cubed. And that's it for this video. Thank you for watching.